And now, I'd like to introduce our presenter. Scott Niemiec is an application engineer with Rohde & Schwarz, supporting the central U.S. from his base in the Chicago area. In addition to his extensive support of spectrum and network analyzers for general purpose testing, Scott is also one of the primary application engineers supporting EMC test equipment and radar test applications throughout the U.S. Before joining Rohde & Schwarz in 2012, Scott was an R&D engineer with Nokia Siemens, and prior to that, he worked as a senior staff RF engineer for Motorola Solutions. He holds a Bachelor of Science in Electrical Engineering from Michigan Technological University. So, without further ado, let's turn our attention to EMI Test Receiver Basics. Is it time to upgrade from your spectrum analyzer? With Scott Niemiec. Hi, Scott. It is all yours. Take it away.
Hello, my name is Scott Niemiec, and I am an application engineer for Rohde & Schwarz North America. And I'd like to welcome you today to EMI Test Receiver Basics. Is it time to upgrade from your spectrum analyzer? We'll start off our discussion about the basic idea of what EMI measurements are, and we'll follow up with exploring the setup and test procedure of those measurements. Then we'll move on to our main topic, the EMI test receiver. We'll start with the hardware and discuss how the receiver hardware is different from a spectrum analyzer. Then we'll look into the details of those dedicated EMI hardware features. We'll talk about the receiver's user interface and how it was designed for the standard and how it's made to make EMI measurements easier. Now that time domain scan or FFT scan has become more commonplace, we'll look at how bring benefits to the EMI measurement. Knowing that EMI debug can feel really overwhelming, we'll walk through a couple of the options on the receiver that has the potential to reduce that debug time. And last, we'll sum it all up with a brief summary of the topics that we've discussed. So let's go on to the EMI measurements. So what is EMI? Let's start with a possible scenario. We are listening to a radio in our office, and the radio station sounds good. Then we decide to print a document. While the printer is running, we notice that the radio station now sounds scratchy. So now we could actually say that station A is bad. We could then turn to a new station, station B, and listen to it. It sounds good, so we could actually say that station B is good. What we witness is that the printer was emitting some noise that interfered with station A. This is EMI, or that EMI is the electromagnetic interference signal emitted by a device. The measurement of this EMI is just one type of the testing that is covered under the subject of EMC, or electromagnetic compliance. Let's look at what EMI measurements is. Starting with the previous radio scenario, let's list the steps we did to find a good station. First was to tune to the station, which is a frequency. Then we listened to the sound of the radio to determine if the station was good. If we wanted to find all the good stations, we could use a function on the radio called scan. The scan function would automatically tune to all the stations and play a short bit of sound out of each station. We can then tune to only the stations that had sound, and once tuned to the station, we would listen to that station for a bit longer than the scan function did and decide if the station was bad or if the station was good. We could use these same steps to find bad stations instead of good stations, or in other words, to find the frequencies that the printer is emitting an interference signal on. Therefore, the steps for measuring the EMI are scan all the frequencies, tune to only the possible frequencies that have EMI noise, which means that we would have to make a list of frequencies where the noise was high enough to possibly cause interference. We can call these frequencies peaks and refer to this list as a peak list. The last step, again, is to listen or measure the power over a longer period of time to know for sure that it's causing an interference. Since this is the last or final step, we'll refer to this as a final measurement. So going over those again, those would be, we would do a scan, a peak list, and a final measurement. Let's make this scenario look a little bit more like an EMI measurement setup. Let's replace the printer with a DUT, or device under test. Then let's replace the radio with a more consistent, accurate measuring device, the EMI test receiver. Now let's go through those original steps again. Scan all the frequencies quickly to find only the possible frequencies. This we can sometimes call pre-scan. The next step is the peak list, which actually is the action of searching the scan trace data to find the peaks. We'll refer to this scanning or searching as a peak search and the final list as a peak list. The last step is to tune to each frequency and measure the power over time, which is the final measurement. Our setup is looking closer to an EMI measurement setup, but we still have a few items to add. Let's start with radiated emissions, which is often referred to as RE testing. As the name implies, the measurement of this energy is radiated or emitted into the air. To receive the measured power emitted from the device, we need to add an antenna to the EMI receiver. The radio and printer example from earlier was a radiated emission setup. The next test setup is for conducted emissions, or CE. The most common conducted path is the power supply lines, where the emissions travel on it. To measure this conducted emission, we need to add a LISN to the supply line. LISNs are a line impedance stabilization network to filter the emissions off into the EMI receiver to read it. LISNs are designed to let the AC power flow through, but couple the emission power off to the EMI receiver. Let's review the EMI measurement section. EMI is electromagnetic interference signals emitted off by a device. EMI can be conducted or radiated. EMI measurements typically have three main steps. Scan, to do a quick pre-scan measurement of all the frequencies. Peak search compares the pre-scan data to a limit line to create a peak list. And final measurement, which measures each of the peaks until the emission is captured completely. Now we'll move on to the receiver hardware design. On the surface, an EMI test receiver will look a lot like a spectrum analyzer. This is understandable since they both share a lot of the same hardware. To understand the hardware differences, we need to understand the differences in the design goals. Let's start at the most basic of design goals. What type of measurements do they do? The primary display on both these instruments plots the frequency on their x-axis. So that means both of these are frequency domain instruments. If we ask the users what is the primary use of a spectrum analyzer, you will find the answer will vary based on who you ask. So we'll leave it open and write down varies per customer. For the EMI receiver, it is different. If you ask, it will almost always say the same thing, and the reply will be to make EMI measurements. Since everyone's trying to get the most value out of their instruments, we'll ask them what is the secondary use for their instruments. Again, for the spectrum analyzer, the answer will vary based on the user. So we'll leave it as vary for a secondary use. When you ask the users what is the secondary use for an EMI receiver, you will likely get a puzzled look or they'll likely repeat the question back to you. You want to know what I use an EMI receiver for when I'm not using it for EMI measurements? The actual answer will more likely be maybe for EMI debug, but mostly I only use it for EMI measurements. Since we already have make EMI measurements for the primary use, we'll just put down EMI debug with an asterisk to indicate that is very little secondary use for most users. Knowing that the EMI test receiver is mostly used for EMI measurement, it makes sense to add dedicated hardware to make those EMI measurements. From the last slide, we know the primary use of EMI test receiver is to make EMI measurements. We can simplify this to a statement that EMI testing is about measuring power consistently to compare to a limit. Therefore, an EMI receiver's goal is to make measurements more consistently. EMI test receivers don't just look very similar to a spectrum analyzer, but actually share a majority of the same hardware. Therefore, we'll start with a diagram of a spectrum analyzer hardware and build on that to create this receiver. Starting on the left, at the RF input, we can see a large section of RF spectrum around the desired frequency will make its way to the mixer, where it could be too much power and cause an RF overload. We can limit the possibility of this RF overload by limiting the RF spectrum. To do this, we can add a bank of selectable filters called a preselector just in front of the mixer. This will reduce the RF power into the mixer. The next hardware improvement is two parts and is implemented in the digital DSP hardware. First is the use of special IF filters, or RBWs, resolution bandwidths, that are narrower called 6 dB or EMI filters. The second is the use of EMI detectors like quasi-peak to improve the measurement per the EMI standards. The last change is to the LO that feeds the mixer. Here we'll add a stepped scan function which enables a step scan of the EMI measurement. Let's compare that step scan to the traditional swept spectrum analyzer. Here we have two different plot views. Notice the plot on the left are frequency versus time, where the plot on the right is the typical frequency domain plot of frequency versus power. First, we'll run the traditional sweep. Notice in the frequency versus time plot that the trace never stops at any frequency but slowly moves past each as it measures them. Now let's compare the step scan. Notice how the time view shows the trace for the step scan to stop at each frequency before moving to the next one. The step scan provides a more accurate measurement at each frequency because it stops at each frequency. And you can see in this section that we are actually at a tuned frequency for a certain amount of time. EMI measurements use special EMI detectors that are time weighted. That means the measured value is determined by how long or by how often the emission power repeats. There are three special EMI detectors: the quasi-peak detector, which is a time-weighted version of the peak detector; the CISPR average detector, which is a time-weighted version of the average detector; and the RMS average detector, which is a combination of the RMS detector and the average detector, which is still also time-weighted. Let's look at how these detectors act over time. Here's a graph of the detector's output versus time, where we'll present only a short burst of pulsed energy. Notice how the detectors changed over time. At the start of the pulse, the EMI detectors didn't report the full power. Only after the power has been on for some time does the EMI detectors report the same as the standard detectors. Once the power is removed, the EMI detectors don't instantly drop down. That is so that if the pulse repeats soon afterwards, the EMI detector would be closer to reporting the value closer to the energy in the emissions instead of the instantaneous. Now, if the peak power was continuously varying quickly like it does in a noise floor, a time-weighted detector like the quasi-peak detector is able to show a value more consistent to the power over time. Because this EMI detectors are time-weighted, they require more time at a tuned frequency to report their values. Therefore, EMI detectors are often only used during the final measurements. For pre-scan, standard detectors like the peak and average detectors are often used to save time in the overall test. Let's review what we've covered in this section. What we learned is that EMI receivers are designed to make EMI measurements. Their goal is to measure power consistently. The EMI receiver is very similar to a spectrum analyzer, but does have some special hardware changes. Pre-selection are used to protect the mixers. Narrow EMI RBW filters are used to improve the measurement at frequencies, and EMI detectors are used with time-weighted. And step scan is used to improve measurement over time. Next, we'll move on to the receiver user interface. Before talking about the receiver's user interface, let's look at where the inspiration comes from, and that's the EMI Standards. The standards define how to make the EMI measurements. From the standards, we also get requirements for the test procedure, like the scan, peak search, and final measurement. The standard even tells us how to use transducers to correct for setup losses and gains. Measurement settings are also listed in the standards. Let's look at the sample standard and list the settings that we can find in the standards. There's detectors, there's bandwidth or measurement bandwidths or resolution bandwidths. There is step size, the space between each frequency point. And there is also measurement times, which is the dwell time to measure at each point. The limit lines are also well defined with multiple frequency ranges and detailed limit levels. One setting that is common for EMI measurement is also the use of log scales. Even the limits are written with log interpretations. Since the EMI receiver is designed to make EMI measurements, let's make a list or checklist of all the settings that we found in the standards. It would make sense that the receiver interface to have direct inputs of these parameters. The screen of the instruments will often show you what setting parameters are available. So let's check the screen of the instruments for settings from our checklist. For comparison, we'll check the screen on the EMI receiver and a spectrum analyzer. Starting with the spectrum analyzer, we can say we found the transducer, so we could check that off of our list. We found the detector settings for our peak detectors, so we can check it off, but since it did not say an EMI detector, we'll list it as a note about EMI detections. Resolution bandwidth, check. But again, it doesn't say EMI, so we'll add a note to the other side. Frequency range, yes. There's a frequency range that we can set. Let's check that off. A limit line, yep. We found a limit line, so we can check that off. I don't see any other settings directly on the screen, but there are a few relatable settings present. The mode equals auto sweep. I know from earlier that sweep and step scan are not the same. So if it lists sweep, then I know it is not using a stepped or scan mode. Well, we will mark scan as failed and detail that in the notes. So scanned, failed. Notes will say swept, not scanned. So I can't find measurement time, but I can find sweep time and sweep points. From these two settings, I could calculate the measurement time per each frequency point and add that to the notes, but mark failed next to the checklist for measurement time. On a similar note, I know the frequency range and the sweep points, so I can calculate actually the step size between frequency points. Again though, adding the calculation comment to the notes, but mark failed in the checklist. I don't see any clue about a search function for the spectrum analyzer. But spectrum analyzers often have some type of peak or marker search, so I'll leave it questionable. So search is questionable. And the other checklist, I don't see any signs of a final measurement. Spectrum analyzers don't have a comparable option, so I will add that to the notes as no. And completely cross it off the checklist. The last item on the list is the log scale. Since the linear scale is actually on the screen, I know we're not in log and log is not being used. Same as the final, that type of feature is not very common in spectrum analyzers. Now let's check the screen of the EMI receiver. I found the transducer again, so I can check that off. And then the settings for the detectors, I found the detector again, but it's a peak. But over on the bar graph, I found the quasi-peak detectors, so I know there is EMI detectors, so I will mark that off, but I'll still leave a note since this is something the spectrum analyzer did not have. And then I'm looking at the measurement bandwidth, and it says quasi-peak, so I know they have EMI bandwidths for the resolution bandwidth, so we can check that off. But again, we'll leave a note since it's something that was not on the spectrum analyzer. And then we find measurement time on the screen, so I can check that off and add a note again since that was not on the spectrum analyzer. The frequency range, again, is the same as it was before, so we can just check that off. Limit lines, I found the limit line again, so I can check that off. And now the new one is at the log scale. I can see I'm using a log scale for the frequency range, so I can actually check that off and add a note that we used a log scale. There is scan labeled on the window, and there's also a scan labeled underneath the stepped for TD scan. So we can write off that this has a scan and add a note since it was not on the spectrum analyzer again. Now there's also a new bar graph window that, if you recall from one of the earlier slides, is a way of doing final measurement. Therefore, we can now check off on the checklist for the final measurements because we have the bar graph. But we still put it over on our notes since it was not on the spectrum analyzer. Note there is a setting for TD scan. This likely means that there is a step size input, but since it doesn't show on the screen, we'll just have to mark it questionable for step size. The last one is for search, and the search we cannot find on the screen either, so we'll leave that as a question mark. Now that we found most of the settings from our checklist, let's take a step back and take a tour of the EMI test receiver's display. There's typically a dedicated mode for EMI measurements. On this instrument, the mode is actually called receiver mode. The receiver mode is a dedicated mode to interface and make EMI measurements. Normally, you'll also see two types of displays. One of the displays is for scan or pre-scan. It will show a more familiar trace view where the frequency scale is logarithmic though. As was mentioned in the earlier slide, the standard detectors are more commonly used in the scan to save time in the test. The other display is a bar graph, which on this instrument, the final measurement display. What makes a bar graph measurement unique is that it is a fixed or setting at a single frequency, making reference to a tune frequency. To help visualize the bar graph's tune frequency, often a marker is added to the scan, and in this one it says TF, and it's overlaid on the scan on the right. The setting bar shows the current settings being used by the receiver. Therefore, it tracks whatever window is active. In this display, the bar graph window is active display because it has a title bar that is bright blue, and the gray title bar of the scan window indicates that it's not an active display. Because of another feature called a scan table, it is possible that the setting bar may not actually show all the settings being used in the scan window. We'll talk about this later when we talk about the scan table. In the earlier slides, we talked about using 3 steps to making EMI measurements. Because EMI test receivers are designed to make EMI measurements, many of the receivers will include a function to automate these 3 steps: scan, search, and final measurement. Here you can see that the automation control window of this receiver. This test automation window will provide a way to automate the receiver to advance through those 3 steps of the scan or pre-scan, the peak search, sometimes labeled auto peak search on other instruments, and the search function is also referenced to as data reduction in some standards. Now that we confirm that there is a search function available, let's check that off on our checklist. The last step, final measurement, is the bar graph measurement, where we would use the EMI detectors, like the quasi-peak detector, to make a compliance measurement to compare against the requirements. Now that we've covered all the overview of the automation controls, we can branch into the settings of each step. We'll start by looking at the control available for the scan step. Note that on the slide, the scan block and the scan table tab were referenced together. So the next discussion will focus on the scan table. The scan table is a list of settings used for the scan window. It is designed to handle multiple frequencies as they are listed in a standard. The scan table provides tables of individual settings for each frequency range. This table provides a way to run one scan across multiple frequency ranges while using different settings per frequency range. If we set up a scan from 150 kilohertz to 1 gigahertz, we would be using the settings from all 3 ranges. First is range 1, range 2, and then lastly range 3. This enabled us to use different settings across the same scan. We used the 9 kilohertz in range 1, we used the 10 megahertz in range 2. In the scan table, there is a direct input setting for step size. Now we can check this off on our checklist that we have a direct input for step size. Notice the step size field, though, is grayed out. And that's because the auto mode is turned on for step. With this on, the receiver is calculating the step size based on the resolution bandwidth, or measure bandwidth. The typical step size is about 1/3 the resolution bandwidth for a normal step scan, and it is 1/4 the resolution bandwidth when you're having time domain turned on. The scan type is where you get to select if you want to use step scan or T domain, which is the time domain or TD scan mode. The Trace Configuration tab is where you select how many traces you want to configure for the scans. There are the typical trace modes: clear write, max hold, view, and etc. But what is different is that each trace now can have 2 detectors. The first detector is used for the scan window. All the different detectors are available, but typically a standard detector is used for pre-scan to save time. The final measurement detector has all the detectors too, but this is where you normally use the EMI detectors for the compliance. Here is also where you'd set the final measurement measure time. Notice how this final measurement section only has 2 settings really, the detector and the measure time. The peak search is where you can set a limit line to compare to a scan trace. The object of peak search is to reduce the trace data to a short list that only includes the frequencies of interest. As mentioned before, this tab is often called data reduction. In the peak search tab, there's 2 main actions. First is to assign a limit line to each trace being used. You will notice that some limit lines are for only certain detectors, like quasi-peak or average detector. The second function is to choose a search mode. Peak search mode will report the top peaks across all of the frequency range. Sub-range is where the screen will be divided equally into multiple sub-ranges, and the top peaks from each sub-range will be reported. Now let's look at the peak list and final results. Looking at the test automation diagram, you can see that there are 2 documents available. The peak list, which is the first frequency list after running the peak search on the scan data. And then there's the final result list, which is the values or final list of values after running the bar graph. Both lists include trace and detectors, frequency and level, and delta to limit. Note that some of them are color-coded to indicate if it's passed, fail, or within the margin. Transducers are the correction or offset values used to adjust the measured power for changes in the test setup. If we have a radiated emission RE test setup, the raw power measured at the receiver is possibly lower than the radiated power being received at the antenna. This is because the power is lost as it travels through the antenna and cable before reaching the receiver. To get the correct measured power reading, we would have to correct or add power to the raw measurement that is equal to the power loss while traveling through the antenna and cable. These corrections are what we call the transducers, and they can be activated in the transducer menu. Notice the example shows that there's an antenna and cable transducer. So you can select a cable and antenna and activate them for the input. The transducers are a table of correction factors per frequency range, or per each frequency. Here's an example of an antenna factor. Notice that there's multiple values for each frequency, and there's a slight graph to show how it changes over the frequencies. An example, though, is that also for antennas, you may adjust from volts to volts per meter. Now, let's take a look at an example of a test automation. Starting with that automation diagram, we can see that in this diagram, we'll go through all the stages. Those stages are the scan, peak search, final measurement and final results. So we'll run a short video showing those. So here we just ran a scan, and now we're doing the final measurements in the bar graph mode on the peaks. Notice how fast it did the scan and peak search. And here is the final results. Let's review the highlights from the user interface section. The EMI receiver's interface is designed to accept values directly from the standard. We are able to check off the checklist that we made of all those values directly from the standard. The receiver often has features to automate the EMI testing measurement. The scan table enables the use of different settings per frequency range in a single scan. Each trace can have up to 2 detectors assigned to it, one for scan and one for final measurement. The peak search uses limit lines to reduce the trace data to only frequencies of interest. Transducers are used to correct measured data for setup influences. Now let's look at one of the more popular enhancements available for the EMI test receiver, and that is the time domain scan. Time domain scan, or FFT scan, is an enhancement to a traditional step scan. We'll show a comparison of the time domain scan versus a traditional step scan. We'll be using the same plots that we used before when comparing the step scan to the sweep. Notice that the left plots use time versus frequency. Now remember, a traditional step scan measures every frequency separate. So as it scans through, notice that it stops and measures each one. On the right, you can see that we actually added filters, overlays, to indicate that each step is being measured separately. Now, a time domain scan can measure multiple frequencies at the same time for each step. Now, notice how the step size and frequency is wider for the time domain scan. And this is because the time domain scan is measuring multiple points at the same time. In this example, we are showing 3 points being measured, but in real life, it could be thousands of points being measured at the same time. The improvement that comes from time domain scan is relative to how many frequency points are measured at the same time. What if the emission is for a short period of time? Now the time domain test time is too short to actually see it. So what is the solution? Well, we can increase the measurement time. If we increase the measurement time so it's the same length, now the time domain's overall test time is the same, but the probability of capturing the emission is actually better because our measured time per step is longer. To enable time domain scan, it is common to have one button to turn it on or off. On this receiver, we actually have a setting for scan type where we can choose T domain or time domain or stepped, which is the traditional step scan. Some receivers offer optimized or extra time domain controls. The one trend is to have a fast or ultra fast time domain scan. In all these cases, these ultra fast time domains are normally not compliant to the standard. And this is because to gain the extra speed, they increase the bandwidth, and by doing so, they decrease the dynamic range because of ADC limitations. Here is a simple graph showing the traditional step scan. And we have the red line indicating the limitation of the ADC. With a very narrow bandwidth, the red line is crossing at the top, which gives us our full dynamic range of the ADC, or almost full. Now if we look at a time domain scan, we'll notice that the bandwidth has gotten wider and our dynamic range has gone down, but it has only gone down a little bit because we're still near the top or near the center of the ADC. But if we increase that too far, now our dynamic range starts to drop significantly to the point that we don't have enough dynamic range to even measure the emission in this spot. So let's review what we covered in this section. Time domain scan is an FFT enhanced version of step scan. Time domain scans use an FFT process to measure multiple points at the same time. Time domain scan can be used to reduce overall test time when using the same measurement time. But time domain scan can also increase probability by increasing the measurement time per point. The last section of this presentation will highlight a couple of the debug tools available in an EMI test receiver. We'll start off with the spectrogram. This is an option that is usually free on a lot of EMI receivers nowadays. Well, a spectrogram is a diagram of the trace history over time. This is very useful for viewing emissions that have time-varying parameters like level or frequency. Sometimes you have heard spectrograms being referred to as waterfall, a plot of the frequency versus time with power levels being color-coded. It is not required for an EMI measurement, but sometimes the action of using it is required just so you can pass the normal test. Here is a spectrogram aligned with a scan window. Notice how easy it is to see the pattern of the signal from the spectrum to the time domain on the spectrogram. So as emissions move or change, we can see in time if they're repeating or coming back. To help understand exactly what a spectrogram is, you go through the process to transform a regular spectrum trace to a spectrogram. The first step is to color map. We'll start with a trace that is monocolored blue, and we'll use a color map to actually color the power levels. So by transferring the colors from the mono blue to individual colors per power level. Notice how the peak around the negative 30 dBm is now yellow. After completing the color mapping though, the next step is to rotate the axis. And so we'll start with the normal axis, frequency versus level, and then we'll rotate it until we get to the spot where we're actually time versus frequency, but the color that we mapped before will now indicate the power level. So now we see time in the y-axis. The spectrogram is a very good tool by itself, but like we saw before, it's a great tool if you combine it with the spectrum view. So if you have the spectrum and you add the spectrogram, you get this nice combination. And this is very useful for synchronizing emissions that might have made it pass or were missed. The next available tool for EMI receivers is RealTime. RealTime is actually a continuous measurement of the frequency span. All of the span's data, all of the frequency, is processed and displayed at the same rate it is captured. Therefore, there is no gaps or it's gapless. This is useful for capturing and viewing emissions that vary over time and that have short periods that are hard to capture. Again, this is not required to do the EMI measurement, but sometimes it's required to do the debug so you can pass your EMI measurement. To better understand real-time, let's compare it to swept and to stepped scans. So swept is a continuously tuning to new frequencies. A step scan is continuously stepping to a new frequency. Real-time does not tune to new frequencies. It measures the same frequency for long periods of time, continuously. This increases the probability of capturing emissions within that bandwidth. But that bandwidth is limited by the real-time analysis bandwidth. RealTime's debug features are that it has a spectrogram. Unlike the last spectrogram, this one is continuous with no gaps, so it's gapless. It has a persistence mode, which is where it takes the spectrum view and overlay it with color coding, and the color indicates how often the trace power occurs over time. This is very useful for seeing signals that are hidden underneath the peak power or other higher power signals. And the last feature is the frequency mask trigger. The frequency mask trigger allows you to actually trigger on a frequency, even if it's lower than the average power or the peak power around it. This way, if you have an emission that is hard to capture, you can trigger on that emission. Let's review the debug section. We started with a spectrogram. Spectrograms are useful for displaying signals that vary over time. We looked at real-time. Real-time is a continuous measurement of the frequency span. That means it is gapless, no missing of the signal within that time. It has a view that is persistence, which is useful for seeing signals that are hidden under other signals. And it has a frequency mask trigger, which is useful for triggering on a frequency when power is around it. We have come to the end of our presentation, so now let's look at a summary of what we've covered. So in summary, the EMI test receiver is designed to do EMI measurements. The hardware is very similar to a spectrum analyzer, but does include some extras, that being pre-selection, EMI filters, EMI detectors, and step scan. The EMI test receiver's interface is designed for direct input of settings from the standards. Included is automation of these 3 steps for EMI measurements. Steps were scan, peak search, and final measurement. Time domain scan is an enhanced version of the step scan that can improve the testing speed or the probability of detection of emissions. Spectrogram and real-time options are useful debug tools. Both of them help you see emissions that changes over time. This concludes the presentation portion of our webinar, EMC Test Receiver Basics. Is it time to upgrade from your Spectrum Analyzer? Before moving on to the Q&A section, I want to take a moment to let you know about our educational webinar series called Everything Test. The webinar series covers the fundamentals of RF, digital, and EMC testing, and from it you will improve your understanding of the basic test and measurement concepts, techniques, and instrument optimizations across a wide range of applications. The series is now available as an on-demand, allowing you to learn at your own pace. To learn more, visit rohde-schwarz.com/everythingtest. Now on to the Q&A section.
All right, well, thank you for that. This was a very good presentation. So again, thank you, Scott, for taking the time to enlighten us about EMI Test Receiver Basics. Is it time to upgrade from your Spectrum Analyzer? And just was looking to see if there were any additional questions. I do see one. Oh, this is someone asking, can we download the presentation from somewhere? So for all that are on and who have signed up, I will usually send out this presentation about 1 to 2 business days after the live webinar, but normally the first of the week. So probably Monday or Tuesday, you all will receive that. At this time, Scott, I don't see no additional questions. Anything else you wanted to touch on?
At this time,
Oh.
I was sorry.
Mm-hmm.
I'm trying to think if there's a question. The question comes up on the FFT, on if it's accepted in standards and stuff. And in most of the standards now, they FFT or the time domain scan is accepted. So it's one of those questions that do come up quite often if it's accepted, and most of the standards, most of the current standards do accept it. So you do have to double check, but that is usually accepted in most of the test scenarios nowadays. So that's one question I always like to make sure that comes out, that people are aware that it is acceptable for full compliance to use the time domain for most testing now.
Okay, I do see a question that did come up. The EMI receiver in your example has a Spectrum tab. So an EMI receiver can also be operated as an ordinary spectrum analyzer. Is that correct?
Yes, most EMI receivers have a spectrum analyzer mode to them. They're commonly built off of spectrum analyzers designs. There's a few receivers that don't, but even the ones that don't, they usually have some kind of spectrum analyzer or real-time mode for them. So they usually can be used as a spectrum analyzer. There is a few limitations usually on some of the advanced spectrum analyzer features that are more single analysis, where there's required wide IQ bandwidth captures. But other than those unique cases like that, a standard spectrum analyzer measurement can usually be done on an EMI receiver, and it usually has a typical spectrum analyzer mold that can be used then.
All right. Again, not many questions. I think your presentation was very thorough, and that might be why I do see some people comment and saying what a very good presentation it was, and good job to you. And I agree, Scott, this was a really good presentation.
Yep.
If mhm.
I was just going to say thanks for all the people that stuck with it. I usually start a little low, so some people drop out because they're like, it's going to be too basic. But I usually try to start a little low so that way we bring everyone up, and then we go over a little bit of each topic. Can always expand on all of the topics later, and then usually end with any questions that helps expand it to what people are looking for. So.
Yeah, I did notice that, and I appreciate that. With me working in the lab, it was really a learning lesson for me that you started there, because I was a little lost. But once you did this, now I'm not saying I'm experienced, but thank you so much. I am now understanding some of this. So thanks again. If we did not get to your question, or if you do have a question after this webinar, please feel free to send your questions to questions@wll.com. You should see it on your screen at the moment, and a member from Rohde & Schwarz will contact you directly with your answer. Again, our thanks goes to you, Scott, for taking the time to enlighten us about EMI test receiver basics. Is it time to upgrade your spectrum analyzer? We are currently working on our next webinar sometime in June. We are in the process with confirming dates and times with the presenters. So please make sure you visit our website to subscribe to our Washington Labs Academy to receive updates. This is easily done by visiting WLL.com. You'll go ahead and click on the training tab in the upper right corner and fill in your information where you see sign up for updates. Well, on behalf of the Washington Labs Academy and Rohde & Schwarz, we would like to thank you for all attending. I will now end the event. Please enjoy the rest of your day, and most importantly, you all, please be safe. Again, thanks everyone. Have a great day.
Thank you.